the next session of my course on solid-state devices of KTU syllabus. We had started a journey to understand the physics of semiconductors. We discussed about the effective mass concept of semiconductors. So from that point, we will move ahead to know more about the physics of semiconductors. We know the construct of an energy band by now. It has a conduction band denoted by CB, a valence band denoted by VB, which is separated by an energy gap denoted as EG, which is also known as the forbidden band. This structure of energy band is such a way that all the electrons are occupied in valence band in normal condition. Since the electrons occupy all the available states in valence band, it cannot move in valence band. And since there is no electron in conduction band, there won't be any current. Now suppose an electron from the valence band escapes to the conduction band. It becomes a free electron. While this electron leaves from valence band, a vacant place is made in valence band, which is known as the hole. This hole can be considered, or the hole is also constituting to the current in a semiconductor. If we apply an electric field, electrons move opposite to the direction of current. The holes in the valence band move in the same direction of the current. How will the hole move? The electrons which is adjacent to it falls into this hole, so that hole takes the position of the neighboring electron. So on and so forth, the holes will move in valence band. This makes the quasi-particle hole. Why it is called quasi-particle? It is not a real particle. It is the absence of electrons. The absence of electrons is called as holes. That is why we call holes as quasi-particles. Though this is a quasi-particle, it has energy. It also have effective mass, and because it is having an effective mass, we can draw the EK diagram for holes. If you remember the EK diagram for electrons, it is of the same shape as the top portion of the figure shown. The bottom portion, which is the inverse of the top portion, is the EK diagram for holes, which states that all energy is opposite to that of electrons. Or in other words, the all energy increases as we go down. Now, with the concept of the EK diagram for electrons and holes, we could see some classification of semiconductor. Before classifying, we should understand that electrons moves from the top of the valence band to the bottom of the conduction band, or the distance between top of valence band and bottom of conduction band is the minimum distance that an electron has to travel to become free, or the distance to be traveled from valence band to reach the conduction band. If the bottom of conduction band is in line with top of valence band, such semiconductors are called direct semiconductors. While an electron falls from the conduction band to the valence band, it releases energy in form of light. So the example of direct semiconductor is gallium arsenide, a compound which is used to make LEDs. If the bottom of conduction band is not in line with top of valence band, it is called as, or it forms indirect semiconductors. Silicon and germanium are example for this indirect type of semiconductors. Since it is the bottom of conduction band is not in line with top of valence band, the electron from the valence band should have a momentum change to reach the conduction band. Since an energy is required for this momentum change, there is no energy that is excess to be released as light. So here it cannot be used, the indirect semiconductors cannot be used for the purpose of LED. So the EK diagram concept have helped us to classify semiconductors into two categories: direct semiconductors and indirect semiconductors. With these scattered basic thoughts, we will move on to some serious discussion on Fermi-Dirac statistics. Why it is statistics? It's because we cannot pinpoint where an electron is. We always discuss about the probability of finding electrons or holes. So in quantum statistics, which is a branch of physics, there is a statistics by the name Fermi-Dirac Statistics, which describe a distribution of particles over various available energy states in system, consisting of many identical particles that obey the Pauli's exclusion principle. Now, what is Pauli's exclusion principle? The Pauli's exclusion principle is the quantum mechanical principle which states that two or more identical fermions cannot occupy the same quantum state within a quantum system. In our earlier discussions regarding valence band, we had mentioned every possible states are occupied by electrons. So we are not new to the term states. The states are the places or the position where the electron can come and stay. Though we discuss more about electrons and holes in case of semiconductors, Fermi-Dirac statistics is not just for electrons or holes. It is for any particles. The only constraint is that they should obey Pauli's exclusion principle. Such particles are known as fermions, particles with half integer spin. So the Fermi-Dirac statistics is a general statistics that cater to any identical particles. And this statistics will help us to find the probability of finding that particle in a particular state. To know more about this statistics, or to know the number of electrons in conduction band or number of holes in valence band, we can make use of this Fermi-Dirac statistics. Now consider the figure from bottom to the top. The bottom position of the figure, we are having G1 states of energy E1. So there are G1 number of states. Every state will have energy E1. And there are N1 electrons available which can occupy these G1 states. The number of electrons available is less than the number of available states. If we move to the top, we see another layer where you have got G2 states of energy E2 of a different energy. Here you are having N2 electrons to occupy these G2 states. The number of electrons here also is less than the number of states available. Likewise, there are I different energy levels, and in each level there are corresponding number of states and corresponding number of electrons which can occupy these states. Now if we pick one energy level, we could explain it with an analogy of having 7 boxes and you are having 5 marbles. You could put one marble in one box. Then what are the different ways, or how many different ways can you fill the 7 box? Mathematically it is equal to 7C5. C stands for combination, permutation and combination, that combination C, which is equal to 7 factorial by 5 factorial into 2 factorial, which is a standard mathematical equation. That equation can be considered to find the number of ways electrons can fill available states. If we pick the ith energy level, the number of states available in the ith energy level is Gi, and number of electrons is Ni. So the total number of combinations will be Gi factorial divided by Ni factorial into Gi factorial minus Ni factorial. As in the previous example of marbles, in place of Gi we are having 7 different boxes. In place of Ni you are having 5, the 5 different marbles. So in order to find the possible combinations, we have 7 factorial by 5 factorial into 2 factorial, which is 7 factorial divided by 5 factorial into 7 factorial minus 2 factorial. Similarly, individual energy levels will have different combinations. So altogether, if we consider all the energy levels and all the corresponding states, the total number of ways the electrons can fill up states will be product of individual combinations or product of combinations in individual energy levels, which is, for example, for energy level E1, the combination possible is G1 factorial divided by N1 factorial into G1 factorial minus N1 factorial. This combination into the energy level 2 combination, which is G2N2 combination. Likewise, we are having n number of energy levels. The product of each energy level combination will give the total number of ways electrons can fill up states, which this is represented by the notation given below, which is pi. We know the symbol of summation. Similar to that, the symbol of products is pi. Pi with I varying from 1 to n, gi factorial divided by ni factorial into gi factorial minus ni factorial. So this is the total number of ways electrons can fill up states in the entire material. If we look deep into the previous equation, it is actually the probability of finding an electron in a state. As in case of tossing a coin, what is the probability of getting heads? This is 1 by 2, because heads is a possibility, tails is another possibility. Total number of possibility is 2. So the probability of getting one possibility is 1 by 2. Similarly, the probability of finding an electron in a state, if we are having Gi states and Ni electrons, always the number of electrons will be less than the number of states. So the probability will be Ni by Gi, which is denoted by a function f of Ei, which is equal to 1 by 1 plus exponential Ei minus Ef by Kt. This is a very important relationship, which is the probability of finding an electron in a state. We know Ei. Ei is the energy level having this number of states. Ef is known as the Fermi level, which is a statistical construct. There is no physical level as Fermi level, but we define a level by the name Fermi level in order to do the calculations. We will see in detail about how we make use of this Fermi level in our later discussions. Here small k is the Boltzmann's constant. We had discussed a different k in EK diagram where I have told that k is not Boltzmann's constant, but here in this probability equation this k is Boltzmann's constant, and as usual capital T is the temperature in degree Kelvin. So the equation F of EI equal to 1 by 1 plus exponential EI minus EF by KT is called as the Fermi function. Now if we put EI is equal to EF in the previous equation. If we put EI is equal to EF, we will have the term inside the bracket of exponential as 0. E raised to 0 is 1. Anything raised to 0 is 1. So this equation becomes 1 by 1 plus 1, which is 1 by 2. So the probability becomes f of e, the probability becomes 1 by 2. Now we could use this for defining the Fermi level. With this knowledge, we could state Fermi level as the energy level where the probability of finding electrons is 50%. There is a 50% chance to find an electron in this level. Now look at the graph plotted. At 0 degree Kelvin, we have a square box which shows that we will find all the electrons below that 0 electron volt value, or when EI is equal to EF. At 0 degree Kelvin, all the electrons will occupy the energy levels below Fermi level. Now if we increase the temperature, say 300 degree Kelvin, we could see a change in the plot. Here on the right side of 0, there are bit of electrons, which means that we could find few electrons in the energy level above Fermi level. If we keep on increasing the temperature, the number of electrons found in the energy level greater than Fermi level increases. So if we go back to the idea of energy band diagram, this Fermi level is a level which comes in between the conduction band and the valence band. In normal condition, all the electrons will be in valence band, which is an energy level lower than the Fermi level. If we increase the temperature, some of the electrons get excited and try to escape to the conduction band. If we keep on increasing the temperature, the number of electrons escaping to the conduction band increases. So the Fermi level gives us the idea regarding different energy levels and the probability of finding electrons in those energy levels. So keep this idea in mind. We will be using it in our coming discussions. Similar to Fermi level or Fermi function, there is another concept called the density of state. What is density of state? The statement which gives the answer is number of states available per unit energy per unit volume is known as density of state. You have to be clear in your mind that electrons cannot just stay somewhere. It can stay only at the permissible available energy states. So the number of states available per unit energy per unit volume is known as density of states. This function is generally denoted by the term n of E. If you remember, the Fermi function was denoted by f, small f of E. Similar to that, the density of state is denoted by capital N of E. And its unit is per electron volt per centimeter. Why centimeter? Because normally for subatomic values or analysis, we use the CGS system. So as an example, if you are having 10 raised to 19 different states for a particular energy, unit energy per unit volume, then the density of state is 10 raised to 19 per electron volt per centimeter, or EV raised to minus 1, Cm raised to minus 1. So that density of state gives us the idea of number of available energy states. Now the question is, why we are studying about Fermi function and density of state, or the number of states available and probability of finding the electrons? It's very simple. If we know these two values, we could find the number of electrons in the conduction band, which is given by the equation integral EC to infinity. EC is the energy of the bottom of the conduction band. From the bottom of the conduction band till infinity is called as the conduction band. The product Ne into Fe, if we integrate with respect to energy with the limits EC to infinity, we will get number of electrons in the conduction band, where Ne is the number of states available and Fe is the probability of finding electrons in these states. I hope you know the basics of integration. Integration is actually the summation. So for every energy state, what is the probability of finding electrons? If you multiply the probability, you will get the number of electrons in that state. Likewise, we find the number of electrons in different states and we just sum to find the number of electrons in the entire conduction band. From the equation, it's clear. N is the number of electrons in conduction band and its unit is centimeter raised to minus 3 per volume. Now let's see how the number of electrons can be found from knowing density of state and Fermi level. The figure shows the density of state of electron on the right side and density of states of holes on the left side. Now if we plot the Fermi level, as you know, for a say 300 degree Kelvin, it will have quite a few electrons above conduction band. The intersection of density of state and the Fermi level, the area between the two curves, one in blue and red, that area will give the number of electrons. Similarly, the number of holes can be obtained from the Fermi level and the density of states of holes. From the figure, if we just see one-to-one multiplication, the point before the starting of density of state graph, we have only Fe. So Fe into 0, those points will be 0. There won't be any electrons. And if we move to the right of the Fermi level, at one point it has become 0. The probability has become 0. There won't be any electrons. So electrons is found only at the place of intersection of these two graphs, one in blue and the other one in red. This is how we find the concentration of electrons in conduction band, concentration of holes in valence band. The study of this concentration of electrons and holes is very important in case of studying the physics of the semiconductors. So we will see more about this in our coming sessions. The next session will cover few of these topics: equilibrium and state condition, effective density of state. We had seen density of state, what effective density of state is. Then the equilibrium concentration of electrons and holes, and concept of excess carriers in semiconductors. So we are moving ahead in case of our discussion on semiconductors. We had seen energy band diagram, EK diagram, concept of effective mass, the concept of Fermi level, and density of state. These knowledges will help us to understand and study more about the concentration of electrons and holes, which are the carriers of current in semiconductor. We shall continue in our next session. Thank you.